pertemuan ke-6 ya, Electrical Engineering. Pertemuan ke-6 Electrical Engineering ya. Capaian pembelajarannya di akhir program studi, mahasiswa diharapkan mempunyai kemampuan merancang dan melaksanakan eksperimen termasuk menganalisis dan menginterpretasikan data secara ilmiah menggunakan metode ilmiah terkait dengan program learning objektif yang ke-8, PLO 8. Di akhir semester, mahasiswa diharapkan mampu memahami beberapa disiplin rekayasa terkait dengan course learning objektif 3, CLO 3. Di akhir minggu, mahasiswa mampu menganalisa perkembangan teknologi teknik elektro yang terkait dengan kemajuan ilmu pengetahuan. Ya, konsepnya electrical engineering, why, what, how, ya, metodologinya flip classroom. Jadi kita banyak diskusi. Baik, lecture note-nya ada di LMS, saya buka. Ya. Sudah kebuka? Ini dari LMS?
Sudah, Pak.
Oke.
Sudah, Pak, sudah.
Ya. Jadi electrical engineering ya, pengantar terkait dengan rangkaian listrik, resistensi, hukum Ohm, hukum kekuatan, rangkaian seri paralel ya, yang mendasari teknik elektro. Ya. Electrical engineering itu salah satu paling mudah untuk memanfaatkan energi adalah dengan menggunakan energi elektromagnetik yang disebut listrik. Cara termudah mendapatkan listrik untuk mentransmisikan ke tempat yang membutuhkannya adalah melalui rangkaian listrik. Electrical engineering itu termasuk model yang memiliki muatan variabel dasar, yaitu arus, tegangan, dan hambatan. Ya. Electrical engineering terdiri beberapa hukum yang mendasari, yaitu hukum Ohm, hukum daya, tegangan, hukum arus Kirchhoff untuk menganalisis operasi ya, di kelas arus searah yang disebut rangkaian seri dan rangkaian paralel.
Electricity powers our world, and we harness it through electrical engineering, the field that focuses on the application of electricity and electromagnetism in our everyday lives. Just as you have blood pumping through your veins, machines and systems often need electrical power flowing through their wires to work. It's the lifeblood of our society, and it's hard to imagine society today without three of the main branches of electrical engineering: telecommunications, power and lighting, and computer engineering. They each came about in their own way, with their own challenges and victories, their own heroes, and sometimes villains. And you'd be surprised how much death is involved in the history of electrical engineering. Well, it can be dangerous. Electrical engineering deals with the properties of electricity and magnetism, so it stands to reason that the field didn't really exist until we knew what those things were. No one had a very good understanding of electromagnetism until English physicist William Gilbert released his principal work, De Magnete, or On the Magnet, back in 1600. After years of experimentation, he found that the needle of a compass points north-south and dips downwards because the Earth is basically a giant magnet. He was the first to describe the phenomena we now associate with electrical attraction and magnetic poles, which is why many view him as the father of electrical studies. Now, electrical conduction, which is the movement of electrically charged particles through a transmission medium, wasn't discovered until around 1729 by a British scientist, Stephen Gray. He discovered it while doing experiments in which he connected a glass tube to various objects, like an ivory ball or a piece of cork, by wire or string. When he rubbed the glass tube, creating friction, he found the object at the other end of the line would be electrified. With the age of discovery and colonization upon the world, could Gray's work be used to produce a faster means of communication? This brings us to the start of the first field of electrical engineering, telecommunication. Efforts to communicate over long distances by things like semaphore were undertaken as early as the 1700s, but it wasn't until 1837 that Sir William Fothergill, Cooke, and Charles Wheatstone patented the first electric telegraph. Their design used 5 or 6 magnetic needles to sway right or left to indicate specific letters. This early model was a little impractical because of its cost, but the men later patented a new version that only used 1 magnetic needle. Their invention was clearly a neat idea, but it didn't really take off until it was used to solve a murder that sounds like it was lifted from the pages of a Sherlock Holmes novel. On New Year's Day 1845, a man named John Towell gave a woman he was seeing a fatal dose of poison. As the poison set in, she started to scream, which alerted the neighbours, and Towell ran off in a panic, thinking he escaped the law as he boarded a train from Slough to London. But his escape was foiled by technology. His description was sent by telegraph to London, where Towell was arrested and later tried and hanged. It's a rather gruesome way to make an invention popular, but it spread the story of the electric telegraph nonetheless. Around the same time as all of this was happening, Samuel Morse was making his own developments in the United States. He figured out how to use an electromagnet with a pen so that when the electromagnet was energized, the pen made a mark on paper. In 1838, he developed a system of dots and dashes, now known as Morse code, so that messages could be easily transmitted. By 1844, he had obtained financial support from Congress and built the first telegraph line in the United States. It travelled between Baltimore and Washington, and on May 24th, he sent the line's first message: "What hath God wrought?" Pretty ominous, if I do say so myself. About 20 years later, in 1866, the British ship Great Eastern succeeded in laying the first permanent telegraph line across the Atlantic Ocean. Before it, large bodies of water were a big obstacle for means of telecommunication. After the transatlantic telegraph line, some engineers began to realise that by fluctuating an electric current, they could induce different sound vibrations. It made them wonder if they could manipulate sound vibrations. Could they input a sound on one end of a telegraph line and replicate the same sound on the other end? Could they capture the human voice? By 1876, they did just that, with the invention of the telephone. A few different minds came up with similar ideas at the same time, but Alexander Graham Bell was the first to get the patent. He was able to use fluctuating current to vary the magnetism in the coil of an electromagnet, which caused a small piece of iron to vibrate on a diaphragm. This replicated the vibration that had initially sent the fluctuation, which reproduced the initial sound. Now, you could talk to people who were far away, but you still needed telephone lines and a phone with a physical connection to them. But that changed when Heinrich Hertz discovered electromagnetic waves around 1887. It was soon realised that these waves could carry a signal by modifying their wavelength, amplitude, and frequency. This led to the radio and the never-ending confusion over who gets credit for inventing it. Now, after World War I, electrical engineers manipulated these signals and found that along with the conversion of light to electrical impulses, they could create a visual broadcast: television. Since then, we've taken these signals even further. With the internet and Wi-Fi, we've developed nearly instant wireless communication around the world. But electrical engineering is far more than telecommunication. We have electrical engineering to thank for supplying power and light. In 1801, Sir Humphrey Davy discovered that he could produce a brilliant spark, or arc, between 2 carbon rods in a battery circuit. This is called arc lighting. Davy's battery wasn't powerful enough to produce a stable arc, so arc lighting wasn't commercially feasible until the 1870s, after Belgian-born engineer Zenobe Theophile Graham developed a generator that could support a higher power capacity. It was called the Graham Dynamo, a continuous current electrical generator that drove the push for electrical power. While arc lighting began showing up on streets around the world, Thomas Edison realised that arc lighting was too bright to be used in the home. This led to his development of the incandescent lamp. By capitalising on the work of many others, his incandescent lighting systems were soon featured at popular exhibits such as the Paris Lighting Exhibition in 1881 and the Crystal Palace in London. But Edison quickly gained competition, most notably from George Westinghouse and Nikola Tesla. This led to what's now remembered as the War of Currents, with Westinghouse and Tesla as proponents of an alternating or AC current against Edison's direct or DC current. Edison did his best to discredit AC currents by trying to convince the public that they were dangerous. He had animals electrocuted by AC currents on public display and even recommended electrocution as a death penalty alternative to hanging prisoners, at which he succeeded. The first person to be executed by electricity was a convicted murderer named William Kemmler, who was put to death in the electric chair in 1890. Despite his other efforts, though, Edison failed to discredit the push for AC. Westinghouse won the contract to supply electricity to the 1893 World's Fair in Chicago, and AC currents have since become dominant in the electric power industry. We also have electrical engineering to thank for many of the electronic devices we use every day. That brings us to the third field of electrical engineering: computers. In their beginning, before World War II, most computers were part of what was called radio engineering. Most of the computers' focus was on radar, radio, and early television. Their primary work was in processing the signals of those devices. Computers only began to gain a broader audience after the transistor was developed in 1947. The point contact transistor was a semiconductor device that could amplify or switch electrical signals. It allowed electrical engineers to replace vacuum tubes, which were bulky, unstable, and consumed too much power. But while the computers could be smaller, they were still pretty large. They also needed a separate integrated chip for each one of their functions. Then, in 1968, American engineer Marcian Hoff helped solve these problems. He conceived of a universal processor that could be used by all computers. His work led to the Intel 4004, the world's first commercial microprocessor. Since microprocessors were so tiny, the computers themselves could be even smaller. And that's how electrical engineers shaped the world we live in today, with telecommunications, electric power and lighting, and computers. The fact is, it takes all three of these fields, none of which even existed until a couple of hundred years ago, to work together for you to watch me right now. So today we explored the history of each of these fields, touching on such topics as magnetism, electrical conduction, telegraphy, lighting, and computers. Crash Course Engineering is produced in association with PBS Digital Studios. You can head over to their channel to check out a playlist of their amazing shows like Braincraft, Global Weirding with Catherine Hayhoe, and Hot Mess. Crash Course is a Complexly production, and this episode was filmed in the Dr. Cheryl C. Kinney studio with the help of these wonderful people, and our amazing graphics team is Thought Cafe.
Insinyur listrik bekerja di berbagai bidang seperti apa? Di logam, lele, menjaga makanan tetap beku, memproyeksikan gambar visual, menyalakan ponsel, lift, naik lift ke puncak gedung percakar langit, bagaimana memindahkan kapal selam melalui kedalaman laut, bagaimana mengembangkan saklar yang semakin cepat, banyak hal, inovasi rekayasa seorang engineer elektrikal.
Electrical engineering is not just one subject. It consists of many different subfields or concentrations. So two people who graduate in electrical engineering might go into two totally different career paths in their own subfield of expertise. The most common subfields you'll hear are power, electronics, which are probably the two most common, then RF or radio frequency, also called telecommunications, and controls. There are other ones that I'll talk about later, but let's dive into what these subfields are, the careers you can get into, elective classes you might take, and senior projects that have been done. Power engineering focuses on the generation, transmission, and distribution of electric power. These engineers could work at an electric power plant when it comes to generating and distributing large amounts of electric power. They could work on solar energy or wind energy. Or they could work on the power, electronics, and battery of electric vehicles. So if you want to make electric cars run further on one charge, then power might be a great concentration for you. So one of the electives you could take is power electronics. This is where you learn about control and conversion of electric power through electronics. For example, an AC to DC converter is a very popular power electronics device. Our wall outlets, at least in most countries, have an alternating voltage, which in turn creates an alternating current, or AC. If you want to charge your laptop, you need a constant voltage, like maybe 15 volts, which causes a direct current, or DC. So how do we go from that changing voltage to a constant one, or AC to DC? Well, inside all of our chargers, there's an AC to DC converter, which are circuits that change the changing voltage into a constant one to charge our devices. You'll learn various circuits that can do this. Don't worry about not understanding what this is right now, just realize you will use circuit analysis techniques and electronics knowledge to then analyze these circuits that have a specific use. You'd also learn DC to DC converters, which are circuits that change one constant voltage to another. They are normally seen in mobile devices to maintain a constant voltage regardless of what our battery level is at. Then, as you can guess, there's AC to AC and DC to AC as well. These can be used in light dimming and emergency lighting systems respectively. Now these can all be used for so many more applications, but all these were the simple ones we can all understand. Power electronics can be seen in audio amplifiers, battery chargers, wind turbines, motors, and so on. There's of course way more to a power electronics class, but it's just too complicated for a video like this. Then you could also take an electric energy conversion class, which is essentially learning specifically about solar energy, wind energy, grid-connected systems, and so on. And there are other classes, but I'm going to move on to senior projects. But remember, every school will differ in the electives that they offer, but this is the overall idea behind the power concentration. Senior projects that students did in the power subfield include an energy harvesting bike that could convert mechanical energy into electrical energy, a solar panel tracker where the lenses could track the sun throughout the day so maximum energy could be converted, and a cell phone charger powered by wind energy via a small wind turbine. So hopefully you have a good idea of what the power concentration is. Now let's move on to electronics. This is about using electrical components to design various devices. These people design and improve our electronics, including computers, phones, radios, TVs, robotics, audio players, medical devices, and so on. This is probably what most people think of when they imagine an electrical engineer. But realize it's easy to look at these devices that use electronics and become interested, but you have to work with the electronics that make it work. You need to make the amplifier circuits, the filters, the oscillators, the logic circuits, etc. So an example of an elective class you might take is filter design, which I want to go into a little detail on. As I said in the computer engineering video, when something is receiving many different signals, like a radio antenna that's receiving many different radio stations at once, how do we remove the unwanted ones? Well, we have a filter circuit that blocks out or filters certain frequencies, but allows other ones to pass through. A simple filter circuit could look like this. Even if you don't know circuits yet, you can still see how simple these can be with just a resistor and capacitor. This removes higher frequencies from a signal, but the consequence of being simple is that it's not very good. It doesn't cut off frequencies very sharply. There are many different radio stations, for example, and let's say we want to listen to 97.3 FM. We want a sharp filter that completely cuts off other stations and just passes the station we're at. If it weren't sharp enough and you were listening to that radio station, you might be able to faintly hear sounds from the other stations because they weren't being totally filtered out, and that would be pretty annoying. So larger circuits are needed which allow for better and sharper filters. It's actually impossible to make a perfect square filter like above, but with more components you can make a very sharp filter that mostly blocks out frequencies or radio stations that you don't want. And this right here is the basics of what a class like this would be like. What values do those circuit components have to be? What frequency would be the center one they are allowing to pass, like 97.3 FM from above? How would changing the values on the left change that center frequency? And how wide would this graph be, or what is the range of frequencies it will allow to pass? If it's too wide, it might let in other stations or frequencies that we don't want to pass through. You can also take an advanced analog circuits class or an op-amp design class, where you learn about other types of circuits like you did filters. But these are kind of tough to explain, like oscillators, phase lock loops, analog to digital converters, and so on. So don't worry about what those are for now. If at the very least you enjoy basic circuits, then you may really enjoy this subfield, because it's just using circuit analysis techniques to create circuits that have a specific purpose. So senior projects that people in electronics did include an analog audio amplifier, which would be used for a speaker, a car alarm system, a heart rate monitoring control system, or an audio distortion circuit that would enhance the quality of sound from an electric guitar by adding certain frequencies into the signal. Now moving on to RF or telecommunications, which is all about wireless communications and high frequency systems. These engineers could work on satellite communications, radar systems, and high frequency electronics for those radar systems all the way to quantum computers. Now this is one of the most math-intensive paths you can go as any type of engineer. So before considering this, make sure you really enjoy calculus level math, vectors, and physics, specifically with electromagnetic waves. Even if you have just taken basic physics in high school, make sure you at least enjoyed the electricity and magnetism portion. So an elective class you could take is digital communications, in which you learn how to take a digital signal and encode it into a wave to be sent off wirelessly. I've shown this animation before in which a voltage signal is encoded into an AM or FM signal. Well, you use that same technique but for a digital signal with ones and zeros, which as you may know from other videos is just a high and low voltage. We can't just transmit that as it is, so we take an alternating voltage and change its frequency for the ones and the zeros. You could also learn how to defend against someone trying to jam your signal by frequency hopping or jumping between frequencies that only your system knows. You could take an antennas course in which you learn about how antennas send signals and different types of antennas. This is a lot of physics and electromagnetic waves, like determining how current in a wire creates an electric and magnetic field at some distance away. Or you might learn how to predict how far a signal will travel based on the antenna parameters. You could take a high frequency circuits class, which could be considered RF or electronics. But let me explain real quick why high frequency is more difficult and different than low frequency. If you attach a rope at a fixed end and started shaking it up and down very quickly, waves would start to travel down the rope. But then reflection would occur once they reach the end, and then those reflections would combine with the incoming waves, and it would get quite complicated mathematically. Well, when you have a very fast changing voltage or high frequency signal, like radio signals, TV signals, and so on, that you put into a circuit, the same thing happens. Current and voltage will travel down the wires, but will reflect back and cause complicated current and voltage equations within your circuit. Way too complicated to explain here, but that's the idea. So if you want to build an amplifier or a filter, it's not exactly the same as before because you have to account for those reflections. And this is another reason this concentration is so math heavy. Senior projects done in RF have included an RFID home lock, so you could open a door with just an RFID card reader instead of a traditional key, a remote controlled dish antenna, an alternative antenna to traditional Wi-Fi antennas for better wireless internet connection, a signal jammer that interrupts a signal from a remote controlled car, and a wirelessly controlled robotic vehicle. And the last main subfield is controls. You really only learn the very basics of this in your required classes, and it is pretty math intensive. Control systems typically use sensors that monitor some output, then those measurements are fed back to something else which makes corrections. For example, your car's cruise control continuously monitors your speed and adjusts accordingly if it changes. Without that feedback of your speed, if your car started going up a hill, the speed would not adjust. Controls can be seen in automatic driving, aircraft flight control, guidance and navigation for cars, ships, aircrafts, and spacecrafts, or temperature control and thermal regulation. Just think simply to air conditioning in the house that measures the temperature and turns the AC on or off accordingly. It's all control systems. The classes are more confusing, so I'm not going to go over those. Just know it is math intensive, but not quite as much as RF. Senior projects and controls include an airport runway heating system that would detect snow and ice buildup to ensure safety of incoming flights, or a seizure detection system, or an electric vehicle steering control system. Now, like I said, there are other subfields that I want to explain briefly as their own category. One being computer. You can specialize on the computer sides of things as an electrical engineer and take some of their elective courses, which I've discussed in other videos. Projects these students have done include a GameCube to N64 controller converter, a surge protector controlled by an Android phone that could turn off the surge protector and monitor electric usage to minimize energy consumption, and a lighting system that is controlled and monitored over Wi-Fi in which mobile devices could control the application. Optics is another subfield. This may be grouped with telecommunications, but I put it separately because it's kind of unique. It's mainly about using light to transfer data. Fiber optic cables use light to transfer data in computer networking as an example, or they can be used in sensors when it comes to sensing something like temperature or pressure. Projects included converting an electric signal to a light signal, then transmitting it through air over a short distance to a receiver. Or an underwater audio transceiver in which visible light communications are used to transmit and receive the sound. And lastly, one more that I want to throw in is digital signal processing. This involves using computers to perform signal processing operations. So instead of having a voltage signal and putting it through a circuit to, let's say, filter the signal like you would in electronics, you have a sampled signal, kind of like taking pictures at various points, and you put it through a computer or digital signal processor to do the filtering, amplifying, and so on with those signals. One project was to create a noise cancelling device, so if someone is speaking into a microphone and there's unwanted noise in the background or whatever, the device could remove that noise. Filtering on a computer has much more power than filtering with just one circuit. And by the way, this is a math-intensive subfield too, because those filtering techniques are all math manipulation. And I'm going to end there because I've thrown a lot at you. So to summarize, various types of people with different interests may go into electrical engineering. You will have the same classes in the beginning where you learn the basics of all the main subfields I've talked about. But then students will find interest in different fields that they'll dive into. By their third or fourth year, students will be taking different elective classes from one another. And they'll also be working on totally different senior projects in their own areas of interest. If any of these interest you, then electrical engineering might be a great major for you. And you don't have to like them all. Many students in power, let's say, really hate RF. So don't worry if you don't like all the subfields. If you like this video, don't forget to like and subscribe, and best of luck on your search.
Apa yang dimaksud dengan electrical circuit? Yaitu sirkuit listrik adalah loop tertutup dari kawat yang menghubungkan berbagai komponen listrik. Muatan listrik mengalir melalui kabel penghantar listrik yang terdiri dari partikel yang sangat kecil yang disebut elektron, yang masing-masing memiliki muatan kecil yang sama, yaitu minus 1,6 kali 10 pangkat min 19 coulomb. Elektron mengalir dengan cara yang sama dari yang potensial tinggi ke yang lebih rendah. Ya. Itulah yang disebut dengan tegangan potensial. Aliran elektron dapat dipisahkan menjadi dua atau lebih aliran yang massa gabungannya sama dengan massa yang masuk. Itu disebut dengan hukum kekekalan massa. Jumlah total elektron yang meninggalkan persimpangan listrik sama persis dengan jumlah elektron yang datang, disebut dengan hukum kekekalan muatan. Ya. Aliran muatan disebut arus dan diukur dengan satuan SI ampere. Ya, satu aliran, 1 coulomb per detik. Ya. Arus listrik mengalir dari positif ke negatif, berlawanan dengan aliran arus elektron. Ya. Muatan listrik dipompa oleh baterai atau generator ketegangan tinggi potensial untuk digunakan dalam komponen listrik seperti lampu, motor, AC, dan kemudian mereka kembali ke baterai atau generator melalui kabel untuk digunakan kembali. Ya. Jenis material berdasarkan hambatan listrik, apa yang disebut dengan konduktor, bahan yang digunakan dalam kabel termasuk logam, isolator, bahan yang tidak memungkinkan aliran listrik yang meliputi bukan logam seperti keramik dan plastik, bahan semikonduktor disebut memiliki sifat antara konduktor dan isolator. Itu yang paling banyak. Ya. Sementara yang 10% beberapa hukum.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at Ohm's law to understand how it works as well as how to use it. There are also 2 problems at the end of this video for you to test your knowledge and see if you can solve. So what is Ohm's law? Ohm's law is a relationship between voltage, current and resistance and how they relate to each other. Ohm's law was developed by a German physicist named George Ohm, who undertook many experiments to develop his theory, including measuring current by touching live electrical circuits to see how much it hurt. As you might imagine, the higher the current, the more it hurt. Now there are 3 formulas we need to use for Ohm's law, but we don't actually need to remember these, and I'll show you a super easy tip in just a moment. So the three formulas we use for Ohm's law are voltage equals current multiplied by resistance, current equals voltage divided by resistance, and resistance equals voltage divided by current. If that seems like a lot to remember, then don't worry, because we don't need to remember them. All you need to remember is Ohm's triangle, which looks like this. So you just need to remember these three letters in order, V, I, R. Then we just write those letters in a triangle with V at the top, and we draw a line to separate the letters. In fact, you don't even need to remember those, because I've made a free PDF guide for you with some worked examples which you can keep on your PC or your mobile and access wherever you need. Links for that can be found in the video description down below. Now all we do when we need to use a formula is cover up the letter we need. So if we want to find the voltage, then we write V equals, and then we cover up the V in the triangle. That leaves us with I and R. So we write I multiplied by R, which means voltage equals current multiplied by resistance. You can write a little multiplication symbol in the triangle between the two letters if it helps you. Now I know what you're thinking, why is current represented with a letter I and not a C for current, or even a letter A for the unit of ampere? Well, the unit of current is the ampere, or the amp, and this is named after André Ampère, a French physicist. A couple of hundred years ago, he undertook lots of experiments, many involved varying the amount of electrical current. So he called this intensity du current, or the intensity of current. So when he published his work, they took the letter I and it became standard until this day. Now you might also come across formulas where the letter E is used instead of V. The letter E stands for EMF, or electromotive force, but don't worry about that. Just stick to using V and substitute V for E if you see it used in Ohm's law questions. Anyway, so by covering V, we get voltage equals current multiplied by resistance. If we want to find current, then we write down I equals, and then we cover up the letter I in the triangle. That gives us V and R. So as V is above the R like a fraction, we can write V divided by R. Therefore, current is equal to voltage divided by resistance. If we want to find resistance, then we write down R equals, and then we cover up R in the triangle. That leaves us with V and I, so we write V divided by I, which gives us resistance equals voltage divided by current. Let's look at some examples for how to use these formulas. First, let's see how we find voltage and how it relates to the other parts. Let's say we have a simple electrical circuit with a battery and a resistor. We don't know what the voltage of the battery is though. The resistor is 3 ohms, and when we connect a multimeter into the circuit, we see that we get a reading of 2 amps of current. We want to find the voltage, so using Ohm's triangle, we can cover up the V, and that gives us V equals I multiplied by R. We know the current is 2 amps, so we can write that in, and we know the resistance is 3 ohms, so we can write that in also. Therefore, 2 amps multiplied by 3 ohms gives us 6 volts. The battery is therefore 6 volts. Now if you want to check your answers for Ohm's questions, then I've built a free calculator on the website. You can just drop your numbers in and it will do the calculation for you. Links for that again in the video description down below. Coming back to the circuit, if we now double the voltage by connecting 2 6-volt batteries in series, we get 12 volts. If we now connect this to the same circuit, the current also doubles from 2 amps to 4 amps. If we double the voltage again to 24 volts, the current will also double to 8 amps. So what's the relationship here? We can see that current is therefore directly proportional to voltage. If we double the voltage, we double the current. Remember, voltage is like pressure, is the pushing force in the circuit. It pushes the electrons around the wires, and we place things like lamps in the way of these electrons so that they have to flow through these, and that causes the lamp to light up. By doubling the voltage, we see that the current also doubles, meaning that more electrons are flowing, and this occurs as we apply more pressure or more voltage. This is just like if we were to use a bigger water pump, then more water will flow. Okay, so what about finding current? Let's say we now have a 3 ohm lamp connected to a 6 volt power supply. To find the current, we write down I equals, and then we cover up I in the triangle. That gives us V divided by R, so current equals voltage divided by resistance. We know the voltage is 6 volts and the resistance is 3 ohms, so the current is therefore 2 amps, and and that's what we see on the multimeter. By the way, if you don't have a multimeter, then I highly recommend you get one. It's essential for troubleshooting, but also building your essential electrical knowledge. I'll leave some links down below for which one to get and from where. So we saw what happens when we use a resistance of 3 ohms in the circuit. But if we double the resistance to 6 ohms by placing another 3 ohm lamp into the circuit, the current halves to just 1 amp. If we double the resistance again to 12 ohms, the current will halve again to 0.5 amps. We can visually see this because the lamps will become less bright as the current reduces from the increase in resistance. So what's the relationship here? We can see that the current is inversely proportional to the resistance. When we double the resistance, the current will decrease by half. If we halve the resistance, the current will double. Current is the flow of electrons, or the flow of free electrons. For us to make this lamp shine, we need to push electrons through it. How do we do that? We apply a voltage across the 2 ends. The voltage will push the electrons. The atoms inside the copper wire have free electrons in their valence shell, which means they can very easily move to other copper atoms. They will naturally move to other atoms by themselves, but this will be in random directions, which is of no use to us. For the lamp to turn on, we need lots of electrons to flow in the same direction. When we connect a voltage source, we use the pressure of the battery to push the electrons through the circuit all in the same direction. For example, to power this 1.5 ohm resistive lamp with a 1.5 volt battery requires 1 amp of current. This is equal to 6,242 quadrillion electrons passing from the battery and through the lamp every second. And if it can achieve this, then the lamp will stay at full brightness. If the voltage or current reduces or the resistance of the circuit increases, then the lamp will become dimmer. Okay, now let's look at finding resistance. Say we have a resistive lamp connected to a 12 volt power supply. We don't know how much resistance is adding to the circuit, but we measure the current as 0.5 amps. To find the resistance, we write down R equals, and then we cover up the R in the triangle. We're left with V and I, so resistance equals voltage divided by current. We know the voltage is 12 volts and the current is 0.5 amps, so 12 divided by 0.5 gives us 24 ohms of resistance. Resistance is the opposition to the flow of electrons. It tries to prevent electrons from flowing. That's why we use resistors in circuits to reduce the current and protect components such as an LED. If we try to connect an LED directly to a 9 volt battery, it will blow out because the voltage and the current are too high. But when we add a resistor into the circuit, then these are reduced, so the LED is protected and will shine brightly. So given the circuit, we can increase the current by increasing the voltage, or we can also increase the current by reducing the resistance. We can also reduce the current by increasing the resistance. Okay, time for you to test your skills. Can you solve these problems? I'll leave a link for the answer and the solution in the video description down below. Problem 1. Let's say we have this lamp which has a resistance of 240 ohms. If we plug this into an outlet in the US, which uses 120 volts, what will the current be? Problem 2. If I plug the same 240 ohm resistive lamp into an outlet in the UK, we get a current of 0.958 amps. So what is the voltage being applied here? Okay guys, that's it for this video, but to continue your learning, then check out one of the videos on screen now and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, Instagram, LinkedIn, as well as theengineeringmindset.com.
Hukum yang mendasari electrical engineering, ya.
Kalau ditanya apa sebenarnya
Resistensi, ya. Rasio penurunan tegangan terhadap arus ini diukur dalam satuan ohm. Hubungan antara arus dan tegangan dan hambatan R merupakan hukum dasar pertama dari model rangkaian listrik yang kita kenal dengan hukum ohm. Ya, resistensi sama dengan tegangan V dibagi I. Ya, ini udah biasa lah ya. Jika V dalam volt, I dalam ampere, R didefinisikan dalam satuan ohm. Ya.
kemudian juga kita harus fasilitasi baik kualitas media. Apakah sebenarnya kita sudah menggunakan media-media ya yang
Muatan listrik dapat memberikan energi untuk menjalankan berbagai macam peralatan listrik. Untuk mencoba itu, ya, berguna mengetahui hubungan antara tegangan, arus, daya yang disebut dengan hukum daya, power law. Ya, power sama dengan arus dikali tegangan.
Ada gamification, ya, ada simulation. Apa itu kita optimalkan karena yang namanya pembelajaran ya tidak semua kita lakukan secara tatap muka, tapi semuanya ada beberapa yang bisa
rangkaian seri, rangkaian paralel. Cara matematis bagaimana kita menentukan tegangan dan arus dalam rangkaian seri paralel yang bertumpu kepada dua prinsip sederhana, ya. Dua resistor dalam satu seri memiliki arus yang sama yang melewati masing-masing. Dua resistor secara paralel memiliki penurunan tegangan yang sama di masing-masing resistor. Ya, hukum seri, hukum paralel.
Nanti kita sudah mengarah kepada yang namanya progress. Kemudian yang kelima, evaluated for impact and outcome. Nah, ini banyak lagi.
Rangkaian paralel menarik lebih banyak arus daripada rangkaian seri. Kawat mempunyai tekanan kecil, disebut tekanan kawat, ya, yang biasanya sebanding dengan panjang kawat dan berbanding terbalik dengan luas penampang kawat. Sedangkan hambatan suatu komponen seperti bola lampu disebut dengan tekanan beban.
Jadi, kalau ditanya apa perbedaannya, kelima ini terjawab, dan ini sudah dilakukan dengan baik. Sebenarnya kita sudah, kalau belum, kita tinggal cek. Gapnya kita dari mana?
Salah satu tugas seorang engineer mungkin adalah memaksimalkan efisiensi penerapan daya, karena efisiensi yang lebih tinggi umumnya menghasilkan biaya yang lebih rendah, dan biaya yang lebih rendah umumnya diinginkan oleh pelanggan. Ya. Sebagai contoh, Edison pada tahun 1879 menerapkan hukum kekuatan dan sebagai hasilnya membuat bola lampu pijar pertama yang berguna. Dia melakukan dengan menyadari bahwa bola lampu hanyalah sebuah resistor yang mengubah listrik, ya, terlebih dahulu menjadi panas, kemudian menjadikan sebagian dari panas itu hanya sekitar 4% menjadi cahaya tampak. Resistor bola lampu disebut filamennya. Kunci dari masalah Edison dalam memaksimalkan efisiensi bola adalah dalam memaksimalkan efisiensi seluruh sirkuit daripada berkonsentrasi pada bola saja.
Lanjut aja ya. Oke, baik Bapak. Oke, kalau gitu saya akan lanjut lagi.
This episode is supported by Prudential. By now, thanks to our lesson on circuit analysis and previous Crash Course Physics episodes, you know your way around a basic DC circuit. You've learned how to simplify circuits with resistors connected in series and parallel with a single battery source, which is great, but a lot of the real-world circuits that you encounter and will have to describe are much more complicated. For example, what happens when there are multiple batteries connected in parallel? And what happens when we add capacitors into the mix with resistors in our DC circuits? On this, our last go-round inside a DC circuit, we'll encounter junctions, loops, and capacitors. Circuits aren't always just a battery powering a set of resistors. The design of a circuit depends on the needs of the system it operates, and we need tools to take any configuration into account. In the mid-19th century, a German physicist named Gustav Kirchhoff expanded on the principles of Ohm's law to improve our ability to calculate current and voltage in complex electrical circuits. Kirchhoff took laws we already knew, the conservation of charge and of energy, and established two rules for circuit analysis. The first rule, which deals with the conservation of charge, is something we've actually already discussed. It's known as Kirchhoff's junction rule, and it states that the sum of all currents entering into a junction is equal to the sum of all currents leaving the junction. Like I've been saying, what goes in must come out. The second rule, based on the conservation of energy, is a little harder to grasp, but trust me, it works. It's Kirchhoff's loop rule, and it says that the sum of all changes in potential around a loop equals zero. So why would you need to know that's a thing? Well, remember, Batteries supply potential, and then that potential, also called voltage, drops across resistors. It's kind of like a ride on a roller coaster. You may climb up steep slopes and fly around the track doing loop-de-loops to your heart's content and your stomach's discontent, but you always start and end in the same place. Likewise, in a circuit, every battery is like a climb in height, gaining potential, and each resistor is a drop. But no matter which way you go in the circuit, you'll always end up where you started. So let's put these rules to the test. Here's a circuit that wouldn't be easy to solve with only Ohm's law. It has 2 batteries and 4 resistors, with a combination of series and parallel connections. You can simplify the 2 resistors in series down to 1, but after that, how do you tackle the rest? If you want to find the current through each branch and the voltage drop across each resistor, you're going to need Gustav's help. The first step of using the junction rule is to label all the junctions. Each junction is a point on a wire that's connected to 2 or more circuit elements. Then you label all the different currents in the diagram. There are only 3 different wire branches, so there are 3 different currents in the circuit. Kirchhoff's junction rule tells us that everything entering junction A must leave it too. Mathematically, this means that I2 is equal to the sum of I1 and I3, since it's I2 that splits off into 2 branches. Notice, by the way, that we've assigned the current directions the way we have, because they make sense with the orientation of the batteries, going from the negative to the positive terminal. But no matter which way you orient them, in your equations, all the values will work out the same way. If you've correctly chosen the direction of the current, then their values will come out positive, like current should. But if you've chosen the wrong direction, then the value will end up being negative. Okay, back to the action. Let's call the equation with the current values equation 1 and return to it later when we need it. Now it's time to try out Kirchhoff's loop rule. You can draw a loop around any part of the circuit where you can imagine a charged particle moving around the circuit in a circle, ending back where it started. To put it simply, wherever there's a loop, we can use the loop rule. We've got one loop in the top half of the circuit and a second loop in the bottom half, and there's actually a third loop here too. It's the entire outside of the circuit. Now you've got your loops and you're going to use them to solve the 3 unknown current values. Let's begin with loop number 1. In this loop, you have one 20-volt battery and 2 resistors, a 5 ohm and a 40 ohm one. You know that there's a voltage gain across the battery and a voltage drop across both resistor 2 and resistor 1. The voltage gain across the battery is 20 volts, but you don't know the voltage drops across the resistors. Thanks to Ohm's law, you can substitute the voltage drop across each resistor with the current times the resistance. Now you've got 2 unknowns in this equation, which we'll call equation 2. Let's set that aside as well. Next, let's look at loop 2. In this loop, you've got 2 batteries and 3 resistors. If you follow the direction of the loop, you see that both batteries add voltage because the loop direction goes from their negative end through to the positive end. Additionally, all the resistors will subtract voltage because the loop goes in the same direction as the current. So it's important to draw your current directions first in order to make this clear. Now you want to do the same thing you did for the first loop, which is to sum up all the changes in voltage to 0. And then you just substitute Ohm's law in for every resistor's voltage to get terms of current and resistance. Now you have this third equation, which we'll call equation 3. While you could go on and create an equation for the third loop, you actually don't need to, because the junction rule gives you an equation to use here. So at this point, you have the 3 equations you need to solve everything. So let's first revisit equation 1 and replace I1 and I3 with equations 2 and 3. Now you have an equation entirely in terms of I2, which you can solve to find that I2 is equal to 1 ampere. Once you have this value, you can easily solve equations 2 and 3 by substituting in the new I2 solution. And there you go. If you wanted to know any of the voltage drops across the resistors, all you'd have to do is multiply the resistance in question by the current passing through that resistor. For instance, the voltage drop across resistor 2 would be the resistance, 5 ohms, multiplied by the current passing through that resistor, which is 1 ampere. That's a total voltage drop of 5 volts. And the drop across resistor 1 in the same loop would be the resistance, 40 ohms, times the current through the resistor, which is 0.375 amperes. That comes out to a voltage drop of 15 volts, which makes sense because then the sum of each drop in the loop is equal to the voltage supplied by the battery. And those are Kirchhoff's laws, the junction rule for current and the loop rule for voltage, with a little Ohm's law utilization as well. Now it's time to reintroduce our old friend, the capacitor. In a DC circuit, a capacitor is useful for storing charge temporarily, then releasing it again later on. But so far, we've been dealing with circuits that have a constant flow of charge, or those that have reached steady state. With capacitors, we deal with transient conditions, or circuit responses that change with time. From our earlier lessons, you know that the amount of charge stored in a capacitor is equal to the voltage across the capacitor times its capacitance. And you can store this charge by connecting a capacitor in series with a battery, letting current flow from the battery into the capacitor until the capacitor's voltage is equal to the battery's. But what happens when you connect multiple capacitors together, like we do with resistors in series and in parallel? Well, if you have several capacitors connected in parallel, the overall capacitance of the circuit increases. In this circuit diagram, we have 3 capacitors connected in parallel with a single battery. Current will flow into the capacitors and will stop when each capacitor holds the maximum amount of charge. So how can you describe the equivalent capacitance of a circuit like this? Easy. The total amount of charge is the sum of the charges held by each individual capacitor. And you know that the charge held by each capacitor is equal to the capacitance times the voltage across each one. And since every point of a conductor has the same potential and all the conductors are connected, all devices connected in parallel will have the same voltage. So you can simplify the charge equation to say that the equivalent capacitance of the circuit is equal to the sum of all the individual capacitances. Note that this is not the same as the parallel equation for resistors. Capacitance is unique in this way. In fact, the convention is also reversed for capacitors connected in series, which will have a lower overall capacitance. For example, if you have a circuit with 3 capacitors connected in series with a single battery, then the current still stops flowing when the total voltage across the capacitors equals that of the battery. The charge contained by each capacitor is the same because current can't flow through the capacitors, only on either side of them. So if one plate of the first capacitor has a positive charge, then the other plate in that first capacitor has an equal and opposite negative charge. This leads the plate of the next capacitor to have an equal and opposite positive charge, since the amount of charge in the plates and the wire that connects them hasn't changed, but the nearby charge plate redistributes the charge to compensate. This effect carries all the way through until the last plate of the third capacitor has a negative charge equal and opposite to the first capacitor's positive plate. So you can picture the entire set of capacitors as one big equivalent capacitor. For devices in series, the voltage drops across each element equal the voltage provided by the battery. So to find the equivalent capacitance in this case, just substitute in the charge equation, voltage times capacitance, for each voltage across the capacitors. The charge contained by each capacitor is still the same, since the charge on each positive and negative plate is the same for each capacitor. Therefore, you can factor out charge and you're left with the equation for equivalent capacitance of capacitors connected in series. So for series capacitors, the combined capacitance is less than the weakest individual capacitor. And guess what? This wraps up our review of electricity. Now all that's left to learn about is the other side of this same force, the realm of magnetism. Today we learned about Kirchhoff's laws and how we can rework conservation of charge and energy to analyze more complex circuits. We also discuss how capacitors function in a typical DC circuit and the ways they behave when combined in series and parallel connections. Thanks to Prudential for sponsoring this episode. The time between when people think they should start saving for retirement and when they actually do is known as the action gap. According to a recent survey conducted by Prudential, the average American starts saving for retirement 7 years later than they think is best. That could cost you $410,675.92 in your lifetime. Another Prudential study found that 1 in 3 Americans is not saving enough for their retirement. Go to raceforretirement.com and see how the action gap affects you. Crash Course Physics is produced in association with PBS Digital Studios. You can head over to their channel and check out a playlist of the latest episodes from shows like Indie America, Shanks FX, and Physics Girl. This episode of Crash Course was filmed in the Dr. Cheryl C. Kinney Crash Course studio. With the help of these amazing people, and our equally amazing graphics team is Thought Cafe.
Hukum Kirchhoff.
Jadi inti satu lagi adalah kenapa kita harus
Hukum pertama, hukum tegangan Kirchhoff adalah salah satu bentuk dari hukum kekekalan energi. Ini dapat dinyatakan sebagai jumlah aljabar penurunan tegangan dalam rangkaian listrik tertutup sama dengan jumlah aljabar sumber tegangan, yaitu meningkat di rangkaian. Suatu tegangan closed loop sama dengan I sigma dari I kali R dari closed loop tersebut dan sama dengan 0, ya. di mana sigma adalah jumlah penjumlahan, misalnya delta P, P1, P2, P3. Ya. Hukum kedua, loop tertutup dapat didefinisikan sebagai jalur apapun di mana titik asalnya dalam loop juga merupakan titik air untuk loop. Ya. Jumlah tegangan dalam loop harus 0. A ke B, ke C, ke D, ya gambar ini A ke B, ke C, ke D, kembali ke A, loop ini tidak independen dari dua lainnya, sehingga tidak memberikan informasi tambahan.
Kita akan lagi ukur individual learning ini, sekarang kita ada di mana, yang kita harapkan.
Jika dua resistor dipasang seri, ada penurunan tegangan pada setiap resistor, ya. Ada penurunan tegangan pada setiap resistor. Tetapi arus yang melalui kedua resistor harus sama karena dia seri. Rangkaian sederhana dengan dua resistor secara seri dengan sumber suplai tegangan disebut pembagi tegangan.
Oke, untuk berikutnya kita mungkin diskusi saja. What is enterprise learning?
Ya.
Jadi
P-out
itu tidak hanya perusahaan ya, Bu, ya.
sama dengan P-in R2 dibagi R1 R2 disebut sebagai pembagi tegangan.
Ini lebih keren sebenarnya.
Ya.
Jadi apa itu enterprise learning? Pertama adalah acquisition of knowledge. Kita harus
Hukum Kirchhoff saat ini adalah bentuk dari hukum kekekalan muatan. Itu dapat dinyatakan sebagai jumlah aljabar dari semua arus pada node harus 0. Ya.
salah satu fungsinya adalah
Sigma dari semua arus setiap titik sama dengan 0, di mana simpul adalah sembarang sambungan listrik dalam suatu rangkaian, dan sigma adalah simbol penjumlahan. Ya.
dia dilakukan secara ya, nah ini cara apa namanya itu kenal ya. Nah, kemudian kalau kita sudah bisa mengetahui apa sih sebenarnya diperlukan oleh
Sigma arus masuk sama dengan sigma jumlah arus masuk sama dengan jumlah arus keluar. Jumlah semua arus yang memasuki node sama dengan jumlah semua arus yang meninggalkan node. Ya. Dalam gambar, kita lihat gambar di sini, yang masuk I1, I2, I3, I, yang keluar I4, I5. Jadi I1, I2, I3 sama dengan I4, I5. Ya.
Nah, jadi seperti yang tadi sudah dijelaskan bahwa memang teori tidak hanya prakteknya susah. Oke, why enterprise learning? Nah, ini kalau kita lihat,
jika dua resistor sejajar, tegangan yang melintasinya harus sama, ya, paralel itu sama. Tetapi arus terbagi sesuai dengan nilai resistensinya. Ya. Pada gambar resisten ekuivalen dua resistor R1 R2. Ya. I1 sama dengan I dikali R2 dibagi R1 tambah R2. I2 yang masuk ke R2 ini adalah R1 dibagi R1 tambah R2 dikali arus yang masuk. Ya, ini hal biasalah. Sudah ini. Oke.